Okay, so Green's first identity here applied to the specific case of this difference of solutions to Poisson's equation more or less simplifies even further, because the first term here involving the Laplacian of this big phi, which is identically 0, drops out completely. Therefore, the whole left-hand side becomes the volume integral of the norm of the gradient of phi, which is a positive number. This cannot be negative. It's a vector length. Therefore, if the whole integral is 0, it means that everywhere in the region of integration, the gradient itself is the 0 vector. Okay? And therefore, the big phi is a constant, a scalar constant. And therefore, phi 1 is at most a uniform shift of phi 2. Any spatial dependence is identical in both. Okay? So said otherwise, under the fulfillment of either Dirichlet or Neumann boundary conditions by that thing, by that big phi here at the boundaries, then essentially the solution to the Poisson equation is unique. Okay, so here you have to reason a little bit what this means. Big phi here is the difference between two solutions. Now we're kind of lifting the theorem one level up. And the theorem, the uniqueness theorem, is this. The solution to Poisson's equation in a given volume V, bounded by surface S, it is unique, okay? Provided the potential obeys either Dirichlet, so in this case you would put the potential to a constant, or the normal derivative of the potential to a constant. And this constant could be not 0, because if I put a constant here, then the big phi has condition 0, right? Because big phi was different between phi 1 and phi 2, but phi 1 and phi 2 obey the same boundary condition. Therefore, big phi is 0, or derivative of big phi is 0 under Neumann. So provided your potential obeys either Dirichlet or Neumann boundary conditions, everywhere on S, mixing is allowed, then the solution to Poisson's equation is unique. Okay? It doesn't mean that it exists. Don't misunderstand what this says. Uniqueness means that if there is one, there is only one. There cannot be two. However, it doesn't tell you that there's not 0. Okay, but in general, yeah, there will be a solution to these equations. Okay, so why is that absolutely critical for your own relationship with electrodynamics and electrostatics? It is because if by any monkey trick you can come up with, any contortions, any acrobatics, any guessing, any stealing, any machinations, whatever, you come up with a solution, you have come up with the solution. Okay? There's no worry to be had that you left something out. So whatever you need to do in order to get to the solution, then it's great, because when you do get the solution, you can with confidence say that your work is done. That's going to be very much the spirit that we'll be following when we study two methods to find solutions to Laplace's equation. Question? The potential, yeah. So just to be absolutely clear, okay. So fundamental thing is this green box uniqueness theorem. We are talking about the electrostatic potential phi. Okay. So here I need as information the charge density rho everywhere. I need a statement from you about the behavior of the potential at the boundaries. And I require you to tell me that either phi is equal to that constant in this region here, or that the derivative of phi in this boundary here is equal to that number. I need this number from you. It's an input. Okay, it's a so-called boundary value problem. You start from the boundary, and then essentially solving the differential equation propagates the information from the boundary back into the bulk. Okay, and you find the whole solution for phi in the bulk from its value at the boundary. People trying to make publicity these days about what they do, which is 19th century mathematics and things like that. They talk about holography and blah, 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 blah. it's just the bloody boundary value problem. Okay. So so that's what it is. Okay. So so you see now the discussion goes a little bit into what we're going to do with all of this, and I'd like to spend. I hope this is clear, right? So you've seen probably uniqueness theorems in the past, and there are some books in which you get one uniqueness theorem after another for different circumstances, for this, for that, for this, for that. And then I've expressed the uniqueness theorem about uniqueness theorems. There is a uniqueness theorem, and that's this one. Okay, so all the uniqueness theorems that you will hear about are special cases of this one. Okay, all the same thing, and it's all coming from that single reasoning, super simple with Green's identity. Okay, but that's the message. The real take-home message here is that if you have found a solution to your Poisson equation, then you are done because you have the unique solution. Okay. Cool. Now, you see, in great books about electrodynamics, and perhaps the greatest of them all is Jackson. You have some introductory material at the beginning, but then you are hit immediately with a chapter entitled Boundary Value Problems in Electrostatics, which is followed by another chapter called Boundary Value Problems in Electrostatics. Okay, and why? Because in a sense, electrostatics is only about solving differential equations as boundary value problems. Okay, and that's what we do. So we're just not going to delve much longer on this for the moment. Okay, so the message here is that